Alright, so now we are going to be starting the radioactivity unit, or it can also be called nuclear chemistry. For those of you who like to follow along in your book, it's chapter 25. First of all, I like to start off with a little bit of review. So first of all, we haven't done this since back in probably October. We need to kind of remember how to write a chemical symbol. To write a chemical symbol, you have to look at the periodic table. If you remember, you write down the element's symbol first. The mass goes in the top right-hand corner as a superscript. The atomic number goes in the bottom right-hand corner as a subscript. So for instance, if you look on the periodic table, you'll see uranium, and on our periodic table, the atomic number is at the top and the mass is at the bottom. But whenever you're trying to write its symbol, you rewrite its symbol as U. You put the 92 for its atomic number in the bottom left, which is a subscript. And then you put the 238, which if you notice I have rounded because we're dealing with the mass number, not the atomic mass, is 238, and it goes as a superscript. Okay, also, we need to kind of remember what an isotope is. This is an atom of a given element with a differing number of neutrons than listed on the periodic table. Remember, to represent an isotope, you have to list the name and then followed by the mass. And again, the mass number, not the atomic mass. So for instance, if we're continuing with uranium, if we're dealing with the uranium from the periodic table, we would have 235, but this obviously isn't 235, it's 238. So we would then call it uranium-238, or shorthand, you can just put the symbol of a U-238. And again, this is the mass number, not the atomic mass. And for those of you who don't remember what the mass number is, it's the number of protons plus the number of neutrons. So now that we've done a little bit of review, let's start talking about nuclear radiation. First of all, it was discovered by Marie and Pierre Curie. They were a couple that were around at the beginning of the 1900s. They came up with the idea of radioactivity, which is the spontaneous emission of penetrating rays either directly from unstable atomic nuclei or as a consequence of a nuclear reaction. Oftentimes, radioactivity will lead to radiation, which is the rays emitted from a radioactive source. Okay, nuclear reactions differ from chemical reactions. In chemical reactions, atoms tend to attain stable electron configurations. Everybody wants to be like noble gas. Everyone wants to follow the rule of 8. So we have ionic compounds that share and steal electrons to get to be a neutral compound, and then we have covalent compounds that share electrons in order to get to be like a noble gas. But in nuclear reactions, we don't have anything like this going on. We have something called radioisotopes. This is a nuclei of an unstable isotope. They are trying to gain stability by undergoing some sort of change. These are usually always accompanied by the emission of energy. They cannot be sped up, slowed down, or turned off. Once it starts, it just has to run its course. That's why it's so dangerous. And they are also not affected by changes in temperature, pressure, or catalysts. So really there's nothing you can do to start the reaction. There's nothing you can do to stop the reaction. You just have to let it continue until it's done. So, stability. Stability of a radioisotope depends on the ratio of protons to neutrons and the size of the nucleus. So, for instance, if you have too many or too few protons, you have an unstable nuclei. So if you look at the periodic table, most of the elements, if you had noticed when we were doing the calculations, are pretty close to a 1-to-1. What that means is, like for instance, magnesium has 12 protons and it has a mass of 24. So if you do 24 minus 12, you get 12. So that means that there's 12 protons and 12 neutrons, which means that it's really stable. All of these elements want to have that 1-to-1 ratio. When you no longer have that 1-to-1 ratio, your technically instability becomes a factor. When an element is unstable because of its ratio of protons to neutrons, we have something called radioactive decay. This occurs when an unstable nucleus releases energy by emitting radiation. Unstable radioisotopes of one element are transformed into stable isotopes of a different element. So just like when we were talking about the octet rule, just like when we were talking about electron configurations, all of our elements, all of our atoms are trying to become stable. If you cannot become stable by following the octet rule, they're going to try to follow a different rule. In this case, they're trying to become stable by losing and gaining protons and neutrons to form a different element. Radioactive decay is spontaneous, which means it just happens at will. Again, there's no really controlling it. And oftentimes it does not require any input of energy. It just naturally happens. So, there are three main types of radiation, and for those of you not taking notes, you would definitely need to be taking notes now, or you might want to be downloading them off of my website, because you're going to have homework here in just a minute talking about these types of radiation. But the first type is an alpha particle. This consists of helium nuclei that have been emitted from a radioactive source, and they can be represented by two different things. First of all, they can be represented by the helium symbol. So if you remember how I just reminded you how to write the symbols, you write the symbol for helium. It has a mass number of 4 and it has 2 protons. So this is one way to represent an alpha particle. The other way is it kind of looks like a fish symbol, but it's actually the Greek letter for alpha. These are the two ways to represent an alpha particle, and you need to remember them. Alpha particles are positively charged because they are just a nucleus. They have no electrons. So if you have 2 protons and no electrons, you're going to have a positive charge. These types of particles are large and do not travel very far and are not very penetrating, which means that all you need to protect yourself from an alpha particle is a piece of paper. Okay? It cannot pass through a piece of paper because it is that weak of a type of radiation. The second type, which is a little bit more harmful than alpha particle, is called a beta particle. It is an electron created from the breaking apart of a neutron in an atom. Basically what happens is a neutron breaks into a proton that stays in the nucleus and an electron which is then released. So if we look at our chemical reaction, we have a neutron that is going to undergo some sort of reaction in which we have a hydrogen and 1 electron breaking off. There are 2 different ways we can represent a beta particle. Just like with alpha particles, we have a chemical symbol that we can use. This E is standing for an electron. It is represented by 0 because electrons have a mass number of 0 because they virtually have no mass, and a negative 1 due to its charge. The negative 1 is actually meaning it's the opposite of a proton. Or the uppercase letter B, which is technically, if you notice, it has a tail down here, and that's because it's the Greek letter for beta. These guys are also negatively charged because, again, we are dealing with pretty much an electron. It has less charge and mass than an alpha particle, so it is also much smaller, but at the same time, it is much more penetrating, which means in order to protect yourself from a beta particle or in order to stop the radiation, you have to be stopped by pieces of wood or aluminum, so you have to have a little bit thicker of a source, and I think actually, if you want to be exact, you have to have 5 to 10 centimeters of wood. Okay, the third type is a gamma particle. This is a high energy photon, which for those of you who don't remember what a photon is light energy. Gamma particles are by far the worst type of radiation. They do not have mass or an electrical charge, so therefore we cannot represent them using a chemical symbol like we could the other 2 particles. The only way we represent them is by their Greek symbol, which is the uppercase letter for gamma, which honestly kind of looks like a Y, and if you notice down here, we kind of have a tail. This is extremely penetrating and dangerous. It can easily pass through paper, wood, and human tissue. The only thing that can be stopped by several meters of concrete or centimeters of lead. So this is the type of radiation that is damaging. This is the type of radiation that you have to wear the lead vest when you go get x-rays taken. This is the kind of radiation that everybody is so scared of, that's so damaging, that we're worried about with nuclear reactors. Gamma particles are by far the worst type of radiation that you can be exposed to. So if you look down here at our picture, alpha particles, look how big they are. They can be stopped by a piece of paper. The reason they can be stopped by something so little is because of their size. Beta particles are a little bit smaller. Again, they're just an electron, and they can go through the paper, but they can be easily stopped by just a piece of aluminum. And if you notice, gamma is technically even smaller because gamma is technically just light energy, and so it can pass through the paper and through the aluminum, but it is often stopped by lead. So now what I'm going to ask for you guys to do, or you're going to begin doing today, you might have some time to finish it up tomorrow if necessary, but you need to make a table organizing the 3 different particles, alpha, beta, and gamma. There needs to be 6 rows of information. The first row needs to be composition. Is it made out of a helium nucleus? Is it made out of an electron? Is it made out of electromagnetic radiation? The second row needs to be its chemical symbol. Alpha particles have a chemical symbol, beta particles have a chemical symbol, gamma does not, so you can just X through that one or leave it blank. The third row needs to be its Greek symbol. What's the symbol for alpha, beta, and gamma? Number 4 needs to be its charge. Does it have a positive charge, a negative charge, or no charge? The 5th one needs to be its penetrating power. For this one, you can simply just rank them, low, medium to high, which one's the highest, which one's the lowest. And then last but not least, we need to talk about shielding. So the 6th row will be shielding. And what I mean by shielding is what material or what types of materials are you going to need in order to block the radiation. So again, today I would like for you guys to start organizing this table. If you need more time, then we'll deal with that tomorrow morning. Please take your time in making this table because this table is going to appear on your test and it is going to be a short answer question. So take your time. Make sure you can read your handwriting, and good luck.